Hello, my name is Allison Vincent, and together with my partners Mary Moody and Rain Richard, we are going to be talking to you today about hydraulic fracturing. We'll be going over the basics of how hydraulic fracturing works, some of the laws and regulations that are in place to monitor it, and we will also be going into detail about several of the environmental concerns related to hydraulic fracturing. So to start off, let's talk about the process of hydraulic fracturing and how exactly it works. A drilling site is chosen based on proximity to underground shale layers that contain pockets of natural gas. Before drilling commences, 4 to 6 acres of land are cleared for the well pad area. The well pad area consists of drilling equipment, a pit for drilling waste, and an area for water storage. A vertical well hole is then drilled anywhere from 6,000 to 14,000 feet deep and is sealed with steel casing all the way down. The top several hundred feet where the well comes into contact with any aquifer layers is further sealed off with concrete in an attempt to prevent groundwater contamination. When the target formation, in this case the shale bed, has been reached, the drill turns horizontally at what is called the kickoff point and continues drilling for a mile or more horizontally, with the borehole continuing to be encased in steel. The horizontal length is then divided into subsections, 3,000 to 5,000 feet long. Starting at the end furthest from the surface, these subsections are then impacted one at a time with a high pulse electrical charge to puncture through the steel casing and into the surrounding rock layers. Water with a trace amount of sand and chemicals is then pumped down into the well. The sand is added to hold the fractures open in the rock long enough for the vapors to seep out, and a variety of chemicals can be used for purposes such as reducing friction and temperature within the borehole, dissolving rock, or killing bacteria, depending upon the needs of the site. This process uses an immense amount of water, as up to 10 million gallons of water can be used per well for each time gas is extracted from it. However, one well can be pumped for natural gas many times, and some wells have been known to produce at an economically viable amount for up to 50 years. As you know, hydraulic fracturing is a very controversial issue. Before we get into the science behind many of the environmental issues associated with it, we wanted to give you a sample of what the natural gas industry themselves has to say. The quotes you see on this slide were taken from a presentation by members of several different natural gas associations. This presentation was given to the Senate Natural Gas Caucus in 2011. Some of the favorable things they had to say about hydraulic fracturing were: it is safe because the groundwater is separated by thousands of feet and tons of impermeable rock and protected by state and federal regulation. A significant amount of water is recycled in the process. Hydraulic fracturing uses a small surface footprint for multiple extended wells. It is clean burning compared to other fossil fuel sources, and the fluid used is only 99% water and sand and less than 1% chemical additives. While the controversy and public awareness of hydraulic fracturing is relatively recent, the process itself has actually been around for much longer than many people realize. Hydraulic fracturing has actually been around commercially since the 1940s. However, technical advances in the 1990s allowed for horizontal drilling, which meant that a natural gas reservoir could be fully utilized with drilling just one well, instead of having to drill multiple vertical wells in several locations. While horizontal wells were a huge technological advancement, they did come with some drawbacks. Horizontal well pads have a larger surface footprint and use significantly more water than vertical wells. However, due to the fact that one horizontal well produces similarly to multiple vertically drilled wells, many people argue that these unfavorable characteristics cancel each other out. Due to this and several other technological advances, shale gas production quadrupled between the years 2006 and 2010 and is expected to be more than 40% of U.S. gas production by 2020. Many of the hydraulic fracturing techniques are now also being used in conventional oil wells due to increasing improved efficiency. The map on the left depicts all of the known shale gas deposits in the continental United States. Looking at this map, as you would expect, hydraulic fracturing mainly occurs in the states of North Dakota, Arkansas, Texas, Colorado, New Mexico, and Pennsylvania. Hydraulic fracturing is banned in Vermont, although there have been no active wells there for some time. The map on the right shows the pipeline network put in place to carry natural gas supplies from drilling areas. And as you can see, the areas with the highest density of pipeline correspond with drilling areas, as mentioned previously. Here we have a list of some of the federal laws that pertain to hydraulic fracturing regulations. The Safe Drinking Water Act contains regulations regarding proper well siting, construction, and operation to minimize risks to groundwater used for drinking purposes. The caveat with this is that it only pertains to hydraulic fracturing in operations where diesel fuel is used. Otherwise, hydraulic fracturing is exempt from these regulations. The Clean Water Act sets regulations for dealing with wastewater disposal. It states that wastewater from hydraulic fracturing cannot be disposed of into surface waters unless the wastewater is of good enough quality to be used for agriculture or wildlife propagation purposes, and disposal must occur west of the 98th meridian. Under the Clean Water Act, hydraulic fracturing is exempt from the necessity to obtain stormwater management permits unless a reportable quantity spill or other water quality issue occurs at a well site. The Clean Air Act establishes emissions standards and reporting regarding hydraulic fracturing. New regulation is being proposed under the Toxic Substances Act that would require information on chemical use at well sites to be disclosed to the public. Public comment has been taken on this proposal and a final decision is expected sometime in 2017. Other applicable federal laws are listed below that apply to hydraulic fracturing in some regard. State oversight is also a very important player in regulation of hydraulic fracturing, and restrictions and standards vary from state to state. State governments, tribes, and local governments are most often responsible for managing surface storage, such as pits and ponds, for wastewater and its disposal. An issue related to hydraulic fracturing that has been in the news lately is the increase in earthquakes and other seismic activity in areas where hydraulic fracturing is prevalent. Contrary to popular belief, however, hydraulic fracturing itself does not cause earthquakes, but rather evidence points to the disposal of wastewater from hydraulic fracturing and other types of oil drilling operations as being the culprit. Around 2 billion gallons of wastewater are injected daily into approximately 180,000 wastewater wells, mainly in the south-central U.S. These injection wells are very deep and deposit these huge volumes of water just above basement bedrock, where old fault lines exist. It is believed then that the water makes its way down through the cracks of these faults and provides lubrication that allows the bedrock to move. A recent incident happened just a little over 2 months ago when a 5.6 magnitude earthquake struck near Pawnee, Oklahoma on September 4, 2016. The vibrations from this quake were felt in 7 surrounding states, and 6 buildings in the Pawnee area were rendered uninhabitable. In response, the Oklahoma Corporation Commission ordered 35 injection wells near the epicenter of the earthquake to be shut down. The Oklahoma Geological Survey recently conducted a study in which they concluded that the rate of magnitude 3 and greater earthquakes in Oklahoma have increased from an average of 1.5 per year prior to 2008 to an average of 2.5 per day. This is a 600-time increase from the historical background. In their report, the Oklahoma Geological Survey also stated that they considered it very likely that this increase has been triggered by increased wastewater injection. The graphic on this slide depicts the incidence of Oklahoma earthquakes from January 2000 to May 2014. The red dots you see are earthquake epicenters, and black dots are injection well sites in Oklahoma. And now I'm going to hand it over to Rain, and she's going to talk to you about hydraulic fracturing and its effects on groundwater.
Before we go into discussing the groundwater issues, let's discuss the background first. So hydraulic fracturing is relatively new, therefore there's not much historical data on contamination effects. Furthermore, there's not much data on the groundwater characteristics in these areas where fracking is taking place. Fracturing occurs at many sites where traditional oil gas reserves are currently or were once fruitful, which means that it's difficult to compare and understand if there was contamination due to the original oil gas reserves and the extraction that was happening then, or if the contamination is due to fracturing. The EPA developed underground injection control program to regulate the wells that receive fluids injected for long-term or enhanced recovery operations. However, due to lobbying, oil and gas production wells were excluded from this. In 2005, Energy Policy Act exempted hydraulic fracturing operations from the Safe Drinking Water Act, except for the injection of diesel fuel. So one of the ways that lobbyists got around this was stating that the underground injection control program was for long-term wells and hydraulic fracturing wells were considered temporary wells. So the hydraulic fracturing basics, this goes in line with what Allison was saying, but to go a little bit more in depth with the fluids themselves and how it works. At first, the shallow aquifers are pierced, and that's where a lot of the contamination occurs. And these fracking fluids are actually very specific to the site due to the site formation, the permeability, fissuring, water saturation, clay content, and capillary effects. Fracking fluids are composed of biocides, clay stabilizers, friction reducers, and high temperature cross-linkers. The flowback waters are only 10 to 40% of the original fluid volume, so some of that fluid does remain down into deep underground. The flowback waters also differ in the composition from the original injected fracking fluid due to reactions that occurred during the injection process. This could be due to high heat, the microbial activity, and the geochemical nature of the formation rock and the fossil deposit. So the groundwater issues are that there's disposal of inadequately treated wastewater to local streams and accumulation of contaminant residues in disposal sites. One of the biggest issues with this is bromide in the wastewater. When bromide is not removed from wastewater streams and gets into drinking water, the bromide in conjunction with the chlorinated drinking water will actually react to create trihalomethanes, which are hazardous. Also, stray gas contaminants, shallow aquifers due to leaking well casings, abandoned oil and gas wells. So these stray gas contaminants, one of the biggest arguments is that some people say, well, there's methane in the area naturally, and that is true. However, there's actually a way to compare methane that is naturally in the groundwater or underground compared to methane that is created due to hydraulic fracturing, and that is by comparing the ratio of methane, ethane, and propane, and then also just using different tracers to compare the two. So other groundwater issues are that you can have high salinity fracturing fluids, and if that gets into water, now you're going to have a very high saline water solution. And just in general, the chemical contamination from the fracking fluids, such as the biocides or the clay stabilizers or the high temperature cross-linkers, and some of those may damage fertility or may actually have damage to a fetus, or may be dangerous to consume, and if these get into the water, it would be dangerous if swallowed. Another issue is overuse of water can lead to depletion and water degradation, particularly in water scarce areas. So even if there is an area that it rains often, but it has not rained recently, or you are pulling more water from the river or wherever the water is coming from, or the aquifer, or your water source, you would be depleting the water source faster than it can be replenished, and so you're creating water degradation. And then also some areas that may have high shale content could be a water scarce area, and now you are depleting what little water there is there. The accumulation of metals is basically due to the fugitive methane can work with the bacterial sulfate reduction, and this actually triggers a reductive dissolution of oxides in the aquifer that would then mobilize redox sensitive elements such as the manganese, arsenic, and iron, and then those would be released into your drinking water supply. Surface water contamination can occur from leaks from the ponds, spills at the job sites, near the drilling pits, and then also just the wastewater storage in general. When you're creating or starting up your fracking fluids, there can be spillage, and this could also just have runoff into the groundwaters. Some of the wastewaters that are produced from this, some states are allowing them to use as dust control mitigation, and when it rains again, then the dust control, the items that were used as dust control actually run off and run off into drinking water supplies. So there needs to be better understanding of what this wastewater actually is. The toxicology issues due to groundwater contamination will be discussed next, and the information is difficult to find. If you actually go to the website that I have linked to the bottom of the table on the left-hand side, this is actually what comes up, and this is supposed to be a site that anyone can go to, and it's supposed to be very friendly and allows everyone to see what kind of chemicals are used in hydraulic fracturing. It's supposed to seem very exposed, but not all of the chemicals are listed. Only some chemicals are listed, and in fact, it only states what the chemical does. It doesn't actually state the harmful effects of the chemical if it is harmful. There are several other sites that you have to go to, such as the EPA TSCA sites, to determine if there is actually a hazard. The next slide that I'll show is taken out of an article, and it actually shows the hazards associated with the chemicals that are used. And like I had stated before, some of the high temperature crosslinkers, may be unsuitable for pregnant women. The other way that industry gets around fracking is that the fracking fluids are used in concentrations that are within the allowable limits. The issue with this is that these chemicals are looked at as separate pieces of the pie instead of being seen as co-contaminants and what the effects of what they can be when they're used together. One other toxicology issue is that the accumulation of these contaminants is not studied very well. So this was the figure I was discussing, where this actually goes through the water fluids for the fracking fluids, and also discusses the issues with them. So recommendations to decrease groundwater contamination. The most basic recommendation is that you should not conduct any type of fracturing within a kilometer distance of drinking water wells. But there are others. For instance, there needs to be baseline water chemistry data in aquifers before shale gas development. You definitely need a baseline. Developing geochemical and isotopic tracers to confirm or refute that there is evidence for contamination. There needs to be water quality changes through time. There needs to be data conducted over the course of the water's life cycle in that area. This would be comprehensive investigation of the hydrology, the hydrogeology, the water chemistry, the sources and mechanisms of water contamination. And then there needs to be more studies done across an extended geographic area, because not all sites are the same, so contamination and how contamination occurs will be different for each site. There needs to be better engineering controls, new engineering controls, and more engineering controls. And for water scarce areas, there should be an alternative water management system, such as not using drinking water, maybe using mine water to be used as part of the fracking fluid. And then also water disposal. There needs to be stricter regulations on the wastewater disposal of fracking fluids, because a lot of illegal dumping still occurs.
Methane is a natural occurring gas, commonly a decomposing byproduct of termites, cows, rotting organics, and rice paddies. It naturally occurs in coal, agricultural soils, and water, and can be found in water and oil wells. It is also a byproduct of fossil fuel burning. Natural gas is about 75% methane, depending on impurities. Methane is increasingly found in groundwater and soils around fracking well sites. Like other hydrocarbons, methane will burn to make carbon dioxide and water. Flaring, the burning of escaping gas shown in the picture, is common in natural gas and oil fields. Methane will not burn in the water, but it bubbles up through the water. You have probably seen videos showing water coming out of kitchen faucets, then set on fire. Homes, mines, and other confined spaces have been known to explode when the methane leaks up through the ground. Methane was meant to be a bridge between coal-burning energy and renewable energies, because it emits half the carbon dioxide as coal and has a shorter lifespan. Methane's 10% leakage rates associated with natural gas production, transportation, and storage is removing its advantages. The EPA has assigned carbon dioxide lifetime as 100 years. Methane lasts for about 12 years. CO2 is currently around 81% of the world's greenhouse gas emissions, while methane is 16%. However, methane traps much more heat. Carbon dioxide is used as the baseline for global warming potential, GWP. Methane has a 72 GWP over 20 years and 25 GWP over 100 years. NASA, NOAA, and the European Space Agency, among others, has been mapping GHGs from satellites. They have shown an increase of methane since 2004 of about 6 parts per billion per year. More detailed studies are being done and using aircraft and ground-level instruments. For example, the Four Corners methane hotspot on the map has shown up for years, yet no one knew exactly why it was there and getting bigger. It was assumed to be from the area's extensive coal mining and oil gas drilling. Detailed surveillance and more precise instruments have shown the methane is primarily due to increased fracking. There is a link to the NASA Caltech study in the references with details of their research and findings. Flaring is a common way to get rid of excess methane in fracking fields. However, it does not burn off all the methane, causing a large jump in methane emissions from 1990. In the case of water wells, methane is vented directly into the atmosphere according to safe drinking water standards. Methane in the ground, under homes, and in mines is pumped out. Flaring is an easy way to see the methane leaking into the atmosphere. There is no easy way to see leakage into the surrounding groundwater or soil. That needs to be done with drilling, excavating, and testing. Flaring does not necessarily mean the well is leaking into the soil or water. Despite that, soil and water are natural sinks for methane. Fracking methane leakage is a growing problem. It occurs in all steps from drilling to transporting to using. Most problems are physical: improper seals, mechanical malfunction, and faulty calibration. While production emissions have gone up, distribution leaks have been on the decline. Some producers are voluntarily upgrading their emissions technologies and systematically checking for leaks. There was a huge uproar, widely covered by the press, of the Aliso Canyon natural gas leak that lasted less than 4 months with 35 metric tons per hour of methane. The University of Colorado found 19.5 metric tons per hour leaking from the natural gas field near Denver for several years. North Dakota's Bakken oil and gas field, a large producer since 2000, leaks enough methane to be detected in Europe, with a total of 275,000 tons in 2014. The highest emitter in the U.S. is Haynesville, Arkansas at 89 metric tons per hour. The Visible Infrared Imaging Radiometer Suite satellite has been monitoring methane flares all over the world. Research has found 90% of gas flared is from just 30% of the sites worldwide. These are known as super emitters. At the Four Corners area, 50% of the methane emissions are from 10% of the sources. At the site of the first commercial fracking, Texas Barnett Shale region, 2% of the facilities produce 50% of the area's methane leaks. Earlier this year, the EPA released its greenhouse gas emissions report, including methane, carbon dioxide, nitrogen oxide, volatile organic compounds, and sulfur dioxide. The causes, trends, and uses from petroleum to agriculture to wastewater were detailed and compared. Mobile sources of methane have decreased by almost 2/3 from 5.6 million metric tons carbon dioxide equivalent to 2.0 in the 24 years shown. Stationary methane, on the other hand, had a high of 8.5 million metric tons CO2 equivalent in 1990 and then a low of 6.6 in 2012. By 2014, methane is almost back to the 1990 high with 8.1. Natural gas emits the highest amount of methane with 176.1 million metric tons CO2 equivalent. These figures do not include captured, flared, or vented emissions. The EPA report also compares the different emitters of methane. For example, the former number one emitter, enteric fermentation, digestion by cows, pigs, horses, did go up 0.1%. While beef cattle populations have been decreasing, dairy cow populations are increasing. They are housed in large factory settings, eating poorly digestible feed. This also helped increase the manure management methane figures by 64.7%. Agriculture accounts for about 52% of greenhouse gas emissions. Landfill gases are about 50% methane, but it is becoming a reliable, renewable source of energy. In the Phoenix area, the City of Glendale landfill sells its generation to Arizona Public Service, and Salt River Project generates electricity from the Tri-City landfill. The World Bank is hoping to restart hundreds of methane emission capture projects around the world, including Brazil, India, Indonesia, and Mexico, through purchase price guarantees. This is a picture of an area in north-central U.S. showing the flares visible from orbit. The Bakken oil field flares enough methane a day to heat 500,000 homes. If you are interested, the link site will show the lights from all over the world. Currently in the U.S., only new fracking sites have methane emissions provision. It is estimated to reduce 510,000 tons of methane just from upgraded equipment and proper maintenance. The EPA is working on provisions for existing facilities, and some states have already implemented stricter methane regulations, such as Pennsylvania. A largely overlooked source of methane is abandoned fracking or gas wells. High-pressure hydraulic fracking can inadvertently reopen abandoned wells. Methane is ventilated into the atmosphere or pushed into the groundwater or soil. Pennsylvania, Ohio, West Virginia, Indiana, Wyoming, and California are leading states actively mapping, capping, and remediating some of the nation's estimated 3 million abandoned wells. States are beginning to require drillers to locate and properly plug, and if needed, remediate abandoned wells before starting any new oil or gas construction.
So our concluding remarks for a safer and cleaner hydraulic fracturing process would be to better regulate the process with exemptions removed out of the regs, have better water monitoring prior to well installs, maybe even monitor water for up to a year or two in advance. Better oversight of the chemicals that are being used and left underground, understand what they do when left for a prolonged period of time. Have there be more transparency of the fracking fluid chemicals by the industry to the scientific community, so co-contamination research can be conducted on those fracking fluid chemicals. Furthermore, better engineering controls and methods for waste containment should be researched and conducted, so pond liners and ponds don't start to leak, so the storage tanks don't leak, and so there are not spills in the area. There should also be a more comprehensive cleanup program for abandoned wells. It shouldn't just be a middle of the night type of drilling method and then you leave the next morning and no one knows what happened. And fracturing should be due to necessity, not driven by profit. This is one of those things that is politically driven and driven by profit. It's unfortunate, but if we can do this due to necessity, it might actually change the process in which fracturing is done.